Hello, my name is Justin, and before I start my presentation on the hippocampus and memory and disease that affects it and the treatment of that disease, I would like to say a few things first. First, I am a sufferer of very early onset dementia. This is why I could not be there today, but thank God we've got the internet. I can do it over the internet for you guys. And lastly, my dementia makes it very hard to remember things, so there's going to be a lot of cutting and pasting of this, so as it follows a straight line while I read my notes and such, you know. Okay, so I hope you enjoy my presentation. The hippocampus. It is a small area of the brain which is often compared in shape to the seahorse. Its name is actually Latin for seahorse, so there's just a little side note there for you. The hippocampus, situated here in this photograph, sits close to the middle of the brain on both the left and right side. It is part of a family of brain components known as the limbic system. As a whole, the limbic system controls body functions by secreting hormones and sending electrical signals, but the hippocampus is different. It is responsible for recording and processing memories and sending them off to be stored in other parts of the brain. In particular, its purpose is to collect and be able to recall memories such as events and the multitude of important facts that are going to be in this presentation, so listen up. This is Henry Gustav Meissen. His inability to form new memories or to remember memories that were formed up to 11 years before the surgery that he got done, and the knowledge of the brain regions removed during the surgery made him prime real estate for the study of memory in connection to certain brain regions. To clarify this, when Henry was 27, he went through an experimental surgical procedure known as a bilateral medial temporal lobe resection. It was conducted in the hopes of stopping his debilitating epilepsy symptoms. During the procedure, parts of Henry's hippocampus, amygdala, and other regions in his temporal lobe were removed completely. When he woke up, he was unable to form new memories or to remember events or names of people that he had met up to 11 years prior to the surgery. However, Henry's case was not able to determine the hippocampus as the main region responsible for forming long-term memories, although it was possible to pinpoint the formation of long-term memory into somewhere within the temporal lobe. In 1962, Dr. Milner published results from trials that she conducted on Henry. During the trials, Henry was made to draw a line between two stars on a piece of paper. He could not look at the drawing though, he had to look at it through a mirror, not directly, such as this person is doing here. She had him repeat this experiment over many different days, and although he couldn't remember having ever done the experiment, he did improve. This shows that his motor skills were improving over time, indicating that motor memory is processed and stored in a different part of the brain to the hippocampus. It is also implied that only memories lost by Henry, such as facts, events, people's faces, and names, are processed within the hippocampus for long-term memory storage. A study was conducted in 1996 following on from the results of the study on Henry. In this study, 3 participants with varying damage to the hippocampus on both sides of their brain and who suffered from rather severe memory impairment were studied. One patient had damage restricted to only the CA1 region, right here, right there. Lost the ability to form new memories post-damage, but still retained all memories that were formed prior to the damage of the hippocampus. The other two participants had more extensive damage to the CA1, CA2, and CA3 region, as well as to the dentate gyrus, this pink area, and the entorhinal cortex, this blue part, suffered not only from post-damage memory impairment, but also lost memories formed prior to the damage. This study is able to show a stronger link between memory and the hippocampus than the case of Henry, previously discussed, because the damage was directly to the hippocampus, not to other brain regions within the general region. Damage to the CA1 region of the hippocampus led only to post-damage amnesia. This leads to the conclusion that the CA1 region is crucial for the formation of new memories for storage as long-term memory, and that it is not important for the recall of old memories. The other two patients with damage to varying parts of the hippocampus had more extensive memory loss. This included the inability to form new memories and the inability to recall events and other information as long as 25 years before the damage. This suggests that memories may take even years to be converted into the long-term memory and stored elsewhere. The past memories that were lost may still have been within the hippocampus awaiting to be stored elsewhere as long-term memories, whereas older memories formed more than 20-25 years before the damage was inflicted may have already been transferred to another part of the brain for storage. Now, relating what we've learnt already to the real world, we now know that the hypothalamus is crucial for forming new memories and for preparing them for storage as long-term memories. But there is a disease that causes the complete destruction of the hippocampus and many other brain regions. This disease is called Alzheimer's. This diagram illustrates the dramatic reduction in grey matter throughout the entire brain of an Alzheimer's sufferer as compared with a healthy brain. This reduction in grey matter makes it very difficult for the patients to plan, think, or keep memories of any kind. But most astounding is the almost complete disappearance of the hippocampus in an Alzheimer's sufferer. This leads to an almost impossibility of forming new memories and makes it difficult to recall old memories. How does Alzheimer's manage to kill the patient's brain tissue? It is actually a protein called beta amyloid. This protein clumps together into plaques which cover the synapses between nerve cells, which inhibits the communication between the cells and causes cell death and brain inflammation. Nerve cells in the brain are thought to die because the plaque that surrounds them causes them to become disabled. This causes immune cells to destroy the nerve cells, thinking that they are no longer useful for anything. It occurs inside of everyone's brain, as nerve cells are trimmed off when they're not used. That's why you have to relearn old things if you haven't used them for a little while. Although, in an Alzheimer's patient, this trimming goes on rapidly throughout the whole brain, uncontrolled. This leads to the death of large areas of the brain because so many nerve cells are being trimmed off and killed. In particular, the hippocampus seems to be the worst in terms of brain cells being trimmed off and dying. Today, there are estimated to be around 30 million people suffering from Alzheimer's, but that number will increase to 90 million by 2050. This shows that we have to act now to come up with treatments for Alzheimer's before we all forget how to live. Some preliminary research published in 2016 into the prevention of the buildup of beta amyloid within the brain through the use of cannabis is showing very promising results. This study was able to show a reduction in levels of the protein beta amyloid within the brain through the use of cannabis. In particular, tetrahydrocannabinol is proven to be very effective in reducing beta amyloid within the brain. In this study, it was shown that cannabinoids produce an acid known as AEA. AEA was shown to promote survival of cells tested in the patients and was able to block the accumulation of beta amyloid within the brain. A reduction of the beta amyloid protein within the brain led to a lower chance of the development of Alzheimer's disease. Because, as discussed before, an overload in beta amyloid proteins is the root cause of cell death within Alzheimer's disease patients. Another study, published in 2005, has shown that a diet rich in omega-3 fatty acids has the ability to reduce the concentrations of beta amyloid protein within the brain. The study consisted of 3 groups of mice. One group was fed control feed, the one on which all of the mice had been brought up on. This diet had a 0.09% concentration of omega-3 fatty acids. Another group was fed a diet that had the same nutritional values as the control, but with no omega-3. The final group was fed a diet with an increased amount of omega-3 fatty acids in it. With a 0.6% concentration of omega-3 fatty acids, this diet had well above the levels of omega-3 within the diet that the mice had been brought up on. Although the change in beta amyloid protein levels within the brains of the mice in the control group and in the group with an increased concentration of omega-3 fatty acids had no statistical significance, the levels of this protein were 77% less in the mice with the diet with high omega-3 fatty acids as compared with the mice with no omega-3 fatty acids in their diet. It was also found that the levels of plaque within the mice's brain was 40% lower in those with the high omega-3 diet as compared with those with no omega-3 in their diet. These decreases in the beta amyloid protein were most significant in the hippocampus and parietal cortex. This is where the largest effects of Alzheimer's disease occur, so there's a link between a high omega-3 fatty acid diet and lower levels of the plaque which cause Alzheimer's. This means a lower risk of Alzheimer's is probable. To finish this off, we have learned through a case study on Henry Gustav Malleisen and a study of 3 patients with damage to the hippocampus that the hippocampus is essential for the formation of new memories and their conversion into long-term memories to be stored elsewhere in the brain. We learned about the major impact of Alzheimer's and how it's caused in a scientific way. We learned about the major impact that Alzheimer's disease has all around the world, and how build-up of beta amyloid protein into plaques in the brain lead to nerve cell death, especially in the hippocampus. We read a study that suggested that cannabis may be able to lower the levels of this protein and reduce the risk of Alzheimer's. And we read a study that suggests that an increase in omega-3 fatty acids within a diet can decrease the amounts of beta amyloid protein within the brain, thus reducing the risk of Alzheimer's. It is clear, though, that a large amount of research is still needed for an actual cure to Alzheimer's, but this is a step in the right direction. Thank you for listening.
Although it was
more extensive damage to the hypothalamus. Oh, hypothalamus!
Please don't tell me that that is completely... Well, I guess we need to do this whole part again. Is it recording? This reduction in grain matter. This reduction in grain matter. This reduction in grain matter. This reduction in grain matter.
In particular, tetrahydrocannabinoids. Tetrahydrocannabinol. Okay, let's just stop that there.
The final group was fed Fe. The levels of this protein were 77% less in the mice with a high omega-3 diet as compared with those that had no omega-3 in their diet. Fuck me. The levels of the
Thank you for listening. Yes! Like me! I'm done! Yes!